Thank you very much, Kate.
All right, thank you. It's a great pleasure to be here. Uh, so the title I had was Scattering in Neutrino Alley, but since this is Astrophysical Week, I decided to make this more specific to scattering of artificial supernova neutrinos in Neutrino Alley. So I'm going to talk specifically about what we can measure with respect of importance for supernova neutrinos. So this, I think, is of known to many of the attendees at this workshop, but I'll just summarize briefly and emphasize a few aspects. So when you have a core collapse supernova, almost all of the binding energy of the resulting compact remnant goes into neutrinos of all flavors with a few tens of MeV energies. That's basically because they can make off with the energy because they barely interact with the matter. This is mostly nu bar pairs in the cooling phase. That's the bulk of the neutrinos that come out over a few tens of seconds. And this is a plot you've probably seen before, the so-called grand unified neutrino spectrum at Earth, showing the different natural and actually one artificial source of neutrinos over many, many orders of magnitude. Supernova neutrinos inhabit this regime here. This is the DSMB that we heard about in the last talk from Thomas, and that is of interest. But of what I'm mostly going to be considering in this talk is a burst supernova, which is when this flux here suddenly shoots up over a period of a few tens of seconds, something like 9 or 10 orders of magnitude. So really, this thing comes and smacks you in the face. And so here's an example. This is an example model. There are many models that are getting more and more sophisticated as advances are made. But this is just an example that shows some of the main features that are present in most of the computed neutrino fluxes from core collapse supernovae. And these shows 3 time phases, first about 50 milliseconds, where what you get is the deleptonization, you get the neutronization burst, you get turn on of electron neutrinos, and then a very bright, sharp spike of electron neutrinos as the neutrons form. And then there's actually this little feature here, a trapping notch, when neutrinos are actually trapped for a short time. In the mid time scale here, up to about a second, you get explosion, and you can see actually reflected in the electron neutrinos some interesting things that are going on here. And then over 10 seconds, you get cooling. And there's enormous information here about what is actually happening in the supernova. And the information is in the flavor, energy, and time profile of the neutrinos. And the visible supernova may not show up for hours or days. Here's another visualization of an example model. This is a Garching, one of the Garching models here with the 3 flavor components, electron neutrinos, antineutrinos, and all the other flavors combined. This is the same 3 time scales as function of energy, where the intensity tells you the neutrinos neutrino flux per bin. And here's another example from the same model family where you actually see a lot of very exciting things happening right at the very end. There's a sharp cutoff due to a black hole formation. When a black hole forms, it tends to be a more energetic flux as well here. So this is what we're after. This is what we want to observe. And what we can learn, all kinds of standard things we can learn. We can learn about the astrophysics, about the core collapse physics, including nucleosynthesis, in fact. We can actually see things happening in real time in the very dense matter and other phenomena. And we can also learn about neutrino physics because it's a very bright source of neutrinos. And we can learn about neutrino mixing, sterile neutrinos, about exotic properties of neutrinos, and so on. And so this is a kind of virtuous circle in the sense that the more you understand about the astrophysics, the better you can learn about the neutrino physics. And the more we have laboratory measurements of neutrino physics, the better we can extract astrophysics. And so here, input from multi-messenger comes this way, and from neutrino experiments that way. And there's also an early alert, which I'm not going to say too much about, but the neutrinos are prompt tens of seconds with respect to the photons, and that allows neutrino astronomers to provide the astronomical community with an alert. So these are supernova neutrino detectors in various different categories here. Water detectors can be made very big, usually because they are made of a cheap material. You get electron antineutrino sensitivity via inverse beta decay. You can get water detectors in the form of imaging Cherenkov detectors like Super K that we heard about, and also long string detectors, which I think we're going to hear more about at this workshop. Liquid argon is sensitive primarily to electron neutrinos. Scintillator also has free protons like water and is sensitive to nu bar, so that's detectors like Juno. You also get coherent elastic scattering in dark matter detectors, and then detectors, there's one example of a detector that is based on lead that is looking for neutrino-induced neutrons from lead that is sensitive primarily to electron neutrinos as well. So here's the table. You don't need to look at all the fine-grained detail of this, but just to get the idea here, this is the number of events that you expect at 10 kiloparsec, the number of neutrino interactions you would see in the detector. The ones that are grayed out have recently completed, and the ones that are green are the ones that have recently started running, and then the yellow ones are the ones that are future ones, including some like Hyper-K, which will have, oops, sorry about that, extragalactic sensitivity. And there's more here. For example, large-scale near-future dark matter experiments will have sensitivity as well. And what I want to say here is that these experiments are highly complementary. We want all of the information possible if a supernova happens. So the big three for the next couple of decades, there's Hyper-K, which is water-based, Juno, 20 kilotons of scintillator, and Dune, 40 kilotons of argon. These have different flavor sensitivities, different sensitivities to different components of the flux. Hyper-K and Juno are primarily sensitive to nu bar. Dune is primarily sensitive to nu E, and this is not a competition. This is a situation where you want as much information as possible, and the whole is more than the sum of the parts. And I want to also say this is really where the measurements that I'm going to talk about come in, is that these are the primary channels. These are the dominant channels for each of these detectors. So Hyper-K mostly sensitive to inverse beta decay on free protons. Dune primarily sensitive to electron neutrinos on argon. But each also has subdominant channels as well. For example, there's electron oxygen 16 charge current channels, which will contribute to Hyper-K, and there are also nu bar channels contributing to Dune. And so what we want to measure, kind of the underlying truth that we're after, that has the information about the astrophysics in it, are the neutrino fluxes versus energy and time for each of the three accessible flavors. And so this is really sort of the picture that we want to get a view of. But what we can measure with neutrino interactions is not perfectly these neutrinos. We only have access to neutrinos via their observed interactions. And so what we can measure are the event rates in the different channels as a function of energy, observed energy, and time. And detectors are imperfect. They have imperfect channel separation and imperfect resolution. So our access to nu E's is via charge current nu E channels. To nu E bars is via nu E bar charge current channels, and then all of them are sensitive to neutral current. And so these are the categories that we actually measure. And so here, this is examples here. Now this is the cross sections convolved with the fluxes to give the same plot here in different detectors, where what I'm plotting here is event rates of observed events. And so this is for liquid argon, and it tracks the nu E's reasonably well. For water, it tracks the nu E bars. Scintillator also tracks the nu E bars, but you can see there's other stuff going on here. There's actually other channels that are present. So for example, there are neutral current channels in scintillator that's making this 15 MeV line here. And so you get different contributions to the scintillator channel, even though it's dominantly inverse beta decay, water is dominantly inverse beta decay, liquid argon is dominantly nu charge current. They've got mixing in of other interactions as well. And so what we need to understand, if we are going to deconvolve, if we want to get the truth here out of the observations as best as possible, of course that will be imperfect, but we need to understand the neutrino interaction cross-sections. So here's a table of neutrino interactions in the supernova energy range. There's charge current interactions and neutral current interactions. The charge current interactions on simple targets here are basically very well understood. The theory of that is several decades old and known to quite high precision. So scattering, elastic scattering on electrons, inverse beta decay on protons, and elastic scattering on protons. Really, we have a good handle on that. We also theoretically have a pretty good handle, assuming all of this is of course assuming there's no nefarious new physics going on. In the standard model, these are all simple targets and well understood. However, when you look at charge current and neutral current interactions on nuclei, these are much more complicated, messy objects. And what you actually see in a detector is various possible things that are spit out of the nucleus, ejected nucleons and de-excitation gamma rays and so on. They can be actually quite messy and complicated final states. And if you're an experimentalist, all you get is those de-excitation products. And what you have to do is try to figure out what is going on. And these cross sections here for the inelastic charge and neutral current interactions of neutrinos on nuclei are not generally very well understood, either theoretically or experimentally. And here's just some examples. So this is an example here of charge and neutral current interactions on oxygen. This is actually a few decade old plot now showing an expected energy spectrum of gamma rays. It's actually not well smeared in the detector, but for this particular study. But here you have, potentially quite complicated final states for a given neutrino charge and neutral current neutrino interactions, and the observables depend on the nuclear physics. So it's something that there are some calculations for, and the calculations are getting better. But really, what we want to do is to measure this. This is something where, if possible, we would like to actually measure what the response of a nucleus is to neutrinos of given energies. Here's another example, and this is one where this paper here has a study of how well it would be possible to extract, in fact, one of the simplest parameters out of a supernova, just the total energy that is emitted from the supernova, which is maybe one of the very simplest thing. And from a measurement in argon, so this would be in Dune, using the charge current interactions. And if you look in the literature for calculations of what this cross-section is, of course, some of them may be better than others, but they basically vary over an order of magnitude. There's a huge range of these cross-sections, and that's because the nuclear physics is not that simple. And if you actually propagate that uncertainty in how well you could extract the total energy, there are enormous. So here, this is if you assume a particular cross-section model and you this is the truth, then you end up with quite large biases in your answer for this total energy. And so once again, it's where the theory, of course, the theory will improve, but really, if we want to get the best possible information out of a supernova burst, we want to measure what the response of the nuclei are. Now, fortunately, nature has given us something that is almost a perfect artificial supernova flux. And this is a stopped pion flux or pion decay at rest flux. And this is the kind of neutrino you can make artificially by slamming protons into a target that make pions, and then the pions, if the pions stop and subsequently decay at rest, you get a very cleanly well understood, a very well understood spectrum of neutrinos with very well understood not only spectrum but flavor composition and timing. And so this comes here just from the fact that this is a two-body decay from a pi plus. The pi minuses all get eaten up by nuclei. The pi plus here will give you a prompt. This is a very fast decay, 30 MeV nu mu. And the muon decaying at rest gives a three-body decay, so you get a range of energy. So this is the prompt nu mu, but you get nu's and nu mu bars over a well-understood range of energies up to half the mass of the muon, and on the time scale of the decay of the muon, which is 2.2 microseconds. And this is a very supernova-esque spectrum. It's a little bit harder than a supernova spectrum. This is just an example of a typical supernova spectrum in these lines over here for the different flavors for NUI, NUI bar, and NUX. And then superimposed here is a stopped pion spectrum. And so you can see there's quite a bit of overlap. The The stop pion energies go a little bit higher in energy. Actually, that's kind of nice because you get a little bit extra event rate. And so if you can measure these neutrinos, you can improve your understanding of actually also what's going on in the supernova itself based on the neutrino interactions and the detection, which is what I'm going to talk about mostly. And there's also other interesting physics reasons to try to understand these interactions as well. Okay, so stopped pion neutrino sources have been used over some decades around the world. Here's some examples of past, current, and future sources. And here is my latest version of a figure of merit plot for comparing these different pion decay at rest sources. And so on this axis here is the neutrino flux per flavor at a given distance. And this is actually approximately proportional to the proton power. It's not exactly proportional, but approximately proportional. The more proton power, the better. And this is the inverse square root of duty factor. And the reason it's the inverse square root is because what you are often interested in is signal over square root of background. And so these diagonal lines are iso signal over square root of background. Now, if I take all the sources from this previous slide and I compute their figure of merit quantities here, what you want to be is up on the right-hand corner. And so what we have here is S and S really occupying that right-hand corner. Some of them are also doing quite respectably, but I'm going to focus here on the spallation neutron source. So the spallation neutron source is a stop pion source at Oak Ridge National Laboratory in Tennessee in the US. This is a facility that was, it's a $1 billion Department of Energy facility, actually not built for neutrinos at all. It was built to do all kinds of other science, material science, engineering, biology, all kinds of things with neutrons. It's a neutron source, so it's basically for scattering neutrons. But it makes neutrinos for free. And the way it makes neutrinos is so the protons come in here, that's GeV protons. The power is actually increasing. I'll say a bit more about that. In very sharply pulsed, very sharp pulses, 400 nanoseconds at 60 hertz. And the protons come into this, this is a meter scale, terrifying mercury target. And this is such an enormous, dense target that almost every pion that is created will immediately come to a screeching halt and decay at rest. And that is actually a fantastic thing for neutrino physics because it means that you get almost no decay in flight. It's all stopped pions. It's greater than 99% pion decay at rest. And so here's the time structure. It's a 400 nanosecond pulse. And so these are the prompt nu mu from the two-body pion decay, pi plus decay, that are in time with the proton pulse. And then you get delayed muon decay neutrinos on a 2.2 microsecond time scale. And this happens at 60 hertz. And what this means is that you get a background rejection factor of a few times 10 to the minus 4. So you know when your neutrinos are coming and you know exactly what their shape is, you know what they look like, and in between you have nothing. And what that means is not only can you only look where the neutrinos are coming, you can also characterize your background by looking off beam pulse. And so all you care about is the square root of the background. In the square root of the background in the pulse. And it's very clean. And so this is from a detailed Jant simulation of the beam. This is the same spectrum here on a log scale. And you can see there's some kind of Schmitz out here, which is coming from things that are not pion decay at rest. There's decay in flight. There's some kaons. Actually, sometimes you might want that. But we actually don't. It's really down by several orders of magnitude. So it's extremely clean, actually unlike the J-Park beam where there's more decay in flight. And if you work out how, yeah. Yes, there is a little bit. It's I actually don't have it. I have another plot where there's the Nui bar on here, and it's like 10 to the minus 4. So it's very small, or maybe even 10 to the minus 5. It's very, very small. I mean, that was the idea of LSND, but we haven't done that experiment. Yep. But it's actually, I think, even cleaner than the LSND beam. Okay, so if you work out what the actual flux is, if you go out to about 20 or 30 meters, and you compare this is the flux you get from the SNS and the neutrino, or the fluence you get in one day from the SNS. Fluence is flux integrated over time. And compare that over to the fluence of a supernova, so the supernova neutrinos integrated over the 10 seconds of the burst. You see that you get at around 20, 30 meters, you actually get about 2 supernovas worth of neutrinos per day. And in fact, the power is going up, the flux is going to be going up, and it's actually going to be even more that. And so what really, it's kind of an artificial supernova we have in neutrino at the SNS that we can use to study neutrinos in the supernova energy range. Okay, so we have a collaboration that is making use of this gloriously beautiful neutrino source, and accidentally, completely serendipitous neutrino source, I have to say. Was not built for neutrinos, was built for neutrons. This is the coherent collaboration. We've got about 100 people from now something like 25 institutions and 5 countries. And we are deployed, we have detectors deployed, subsystems deployed in a basement of the spallation neutron source. This was also a piece of very good luck. There happened to be a storage area in the basement of the SNS along the beam. So this is where the proton beam comes in. This is where that mercury target is. The neutrinos just come out isotropically from the target, and all we have to do is bathe in their glow, sitting there in Neutrino Alley here. And so these are the detectors here. So that's what it looks like looking down Neutrino Alley. These are the detectors that we currently have deployed. Actually, this one is now, Mars is now over in the alcove over here. And we have many future detectors that I'm going to say a little bit more about soon. Okay, and in fact, the primary goal of this experiment was to look for coherent elastic neutrino nucleus scattering, or sevens, that I mentioned briefly as something that is in fact in the standard model quite well understood, but had never been measured for a long time. This is when you have a neutrino that smacks a nucleus by exchange of a Z boson, its neutral current, and the nucleus recoils as an intact entity. And this is, you can think of this as the nucleon wave functions and the target nucleus being in phase with each other. The hallmark of coherence is that the total cross-section scales as a single constituent cross-section times the square of the number of constituents. And so in this case, a constituent is in fact, a constituent is more like a neutron. And quantitatively, this condition holds when the momentum transfer times the size of the nucleus is very small. And in fact, this is something that for neutrino energies up to about 50 MeV for a medium-sized nucleus, there's a fairly high degree of coherence, and you'll have a, this sevens is the dominant interaction. And coherent collaboration, so sevens is not the topic of this talk, but I will still say something about it, since in fact it's kind of the primary purpose of the coherent experiment. So this here is a plot of the cross section. The sevens cross section is a function of neutron number. So the weak charge of the nucleus is held primarily by neutrons, and so you expect the sevens cross section to scale as n squared. And so this is what you expect, in fact, is this line here. There is, in fact, a form factor. The nucleus is not perfectly point-like. In fact, it has a shape, and if you take into account that shape, you get a suppression of the sevens cross-section, of the coherent cross-section, and that's shown in this green line. The width of this green line is plotted here is shows the uncertainty on the form factor. It's basically, the width of this is the uncertainty due to the form factor uncertainty of the sevens cross-section. So you can see that the nuclear form factor uncertainties are small. So Coherent made the first measurement of sevens in 2017 on a cesium iodide. This was a 14.5 kilogram cesium iodide crystal. And this error bar, in fact, represents the full data set of that measurement, and you can see it is consistent with the standard model, maybe a little bit, tiny bit low. The second measurement of sevens was in argon. That was in 2020, and that's that measurement here in a 22.5 kilogram single phase liquid argon detector. And you can see it's also consistent with the standard model within 1 sigma, a little tiny bit high. We now have a new measurement. This is brand new this year of sevens on germanium. This is with, we actually have 18 kilograms and 5 were deployed in a run last summer. And of this, this run, we have a cross-section. It's actually about 1.8 sigma low, but within 2 sigma of the standard model. And this is our new result. And we're running again this summer with germanium. And so if you want more information, here's a little tiny bit more about the coherent germanium result. These are the data sets. These are the beam, on-beam, so this is energy and time. We can use both the energy and the time in germanium. Germanium has somewhat slow timing, but we can still, it's still approximately microsecondish, so we can use it. And superimposed on here is the standard model expectation. These are the off-beam measurements, which we use those to subtract the background, which is actually relatively small for germanium, and this is what gives us a result. It's a total of 21 events compared to about 35, I think it is, expected from the standard model. And so here are the uncertainties. This is statistically dominant. Okay, so what is for the future in Neutrino Alley? So here's the sevens n-squared plot. We are taking much more data with germanium. That's starting this summer. In fact, we're preparing for the another run starting in before the end of the summer with the full 18 kilograms of germanium. We have funding. In fact, it's mostly Korean funding for a 750 kilogram single phase argon detector, so an upgrade of our 22.5 kilogram detector. And this is the detector's coming to Oak Ridge in the summer and will be deployed, should be taking data next summer, 2025. We have 2.5 tons of sodium iodide, of which about half is deployed now. And this is the smallest, much smaller target, so you get higher energy recoils. And then we actually recently had some good news that this is now funded by NSF, a 10 kilogram cryogenic cesium iodide crystal. Cryogenic allows a lowering of the threshold by a factor of 2. Using undoped cesium iodide, you can get much higher light yield and lower thresholds. And so we're still exploring this n-squared curve. But more relevant for supernova, of course, actually sevens is relevant for supernova since you get sevens in dark matter detector. But more relevant for supernova neutrinos, directly relevant, is what we call incoherent. We call it inelastics. So we sometimes call this incoherent. These are interactions where you actually have a high energy event, where you have a charge or neutral current event where you get, if it's a charge current event, you get a lepton. If it's a neutral current event, you will usually get only some kind of de-excitation debris. And we in fact have a whole bunch of materials that we have taken data already. In fact, there's the status here. We have 2 published results on lead and on sodium iodide. And then we also have a whole bunch with data in the can, not yet analyzed, and we have, or under analysis right now, and we also have various proposals. And the ones in red, which is most of them, are especially red for supernova neutrino detection. We have argon detectors, and we have lead, and we have water. And so I'll just zoom in a little bit. I guess don't have too much time left, but this is what we have for our current and future coherent inelastics detectors. We have a 250 kilogram liquid argon TPC. This is in the proposal stage. It is not yet funded, but this is something that is very Dune-like and will, in fact, tell us the detector response for something that looks very much like Dune. And so it is a kind of calibrator of detector response as well as cross-section. We have also some new Japanese collaborators who are planning, in fact, a 10-ton scale light water detector that is focused on the inelastics in oxygen, so charge and neutral current interactions in oxygen. And they are planning a small baby detector to measure backgrounds, in fact. We have a lead glass. This is a prototype here, and we have made one measurement of neutrino-induced neutrons on lead, which came out, in fact, rather anomalously low compared to theory. And to further test that and see the lepton as well, we have a lead glass detector, which is now, there's one prototype deployed, and we would like to proliferate that as well. This one is not really, maybe not so supernova relevant, But we're also looking into, we have a measurement, actually data in the can, for neutrino-induced fission of thorium, which is something that has never been measured. So this is charged current-induced fission of thorium, and this detector is called NuThor. And we also are able to do in our SEVENS detectors, even though those detectors are really optimized for very low threshold interactions. They're looking for tens of keV energy deposition, whereas inellastics will typically, supernova charge and neutral corona events will typically deposit energy of the scale of the supernova neutrinos, so MeV, tens of MeV scale. So that gives some practical difficulties in the detectors. The detectors tend to be optimized for looking for very dim, faint little blips, whereas, and so to those detectors, a supernova charge current on argon, for example, would look like a blazing, brilliant, bright event, and that requires some attention to the design of the detector to have the dynamic range to see both the little teeny blips and the blazing bright events. However, we are able to do that at some level in our smaller argon detector. There's people trying to extract that information. And in the new single-phase R detector, the dynamic range will be sufficient to see that full range. We are also, in fact, sodium iodide in particular, we already have one measurement in sodium iodide on the iodine 127, and we will be able to replicate that in very large statistics in a much larger detector. And then there's some events, the detectors are small, the inelastic event rates are much lower, but we will still explore them in the other detectors. I want to make one mention of the heavy water detector. We have a heavy water detector in Neutrino Alley. And the idea of this detector is to look at this cross-section interaction. This is the one used in SNO, basically the charge current breakup of nu-E on a deuteron. And what you get is an electron with almost the energy of the neutrino. And this is a cross-section which is theoretically well known, in fact, to a few percent. And so the idea, our current dominant uncertainty on all of our measurements so far is the uncertainty on the neutrino flux normalization. We know the shape of the spectrum very well, but the normalization is about 10% uncertainty. And the idea is that if you can measure the flux with a well-known cross-section, then that will reduce the flux uncertainty for all of our detectors. And we have, in fact, one heavy water detector deployed with some data in the can and being redeployed this summer, along with a a light water module. There's a nearly identical module containing light water, where the idea is to actually go after these inelastics on the oxygen 16, which is common to both the heavy and the light water, to allow subtraction, both understanding of it in itself, but also to reduce the systematics for this lower energy part of the deuteron, electron-neutrino deuteron cross-section. And so this light water module is under deployment this summer. And so we have a lot going on. The power at the SNS is being increased. It's going up to 2 megawatts very soon, and in fact, in the next decade or so, there will be a second target station. This tends to be getting pushed back a little bit, but it will eventually come. And eventually 2.8 megawatts distributed between the two detectors. 3/4 of the protons are going to go to the first target station here. This is looking down. This is where the protons come in. This is where Neutrino Alley is here. This is the second target station, but we are very actively exploring the possibilities for siting detectors either between them, new sites near the first target station, and potentially more space, even though lower flux near the second target station. So there's actually, I didn't talk about it, but we actually have very many interesting possibilities for looking at accelerator produced dark matter as well. Okay, so I think I am exactly on time. So here are the takeaway messages. For supernova neutrinos, we want to catch them all. And we also, in order to catch them, to do something with them once we have caught them, we need to know what the cross-sections are. And so there's really enormous science to be gained, and the way we can understand the cross-sections is by having an artificial supernova. That is, in fact, what we have in Neutrino Alley. It's an almost ideal supernova calibrator There are many, many measurements going on, and we hope to have, I hope, and we're cranking them out already at the rate of a few per year, and I hope that will continue for many years to come, and even more and better. So I will stop there.
Okay, time for questions, comments. Francesco, then I have.
Yes.
Thanks, Kate, for this beautiful program, Kate. So I wonder, so of course you have other physics program that you also mentioned in the beginning. For instance, LSND, before somehow running it into this result, 30 years ago had as a goal measurement of proton strangeness. Garvey explained
Yes.
that you want to measure. However, this will require a scintillator, and it's not within your program.
We have discussed it. We of course have too many things to do at once. That actually is on the list. Looking at proton scattering. I mean, there you get axial, very nice probe of axial interactions. It just hasn't quite gotten to the top of the queue. There are challenges with particular challenges with scintillator. But yeah, that is definitely on our list of, there's actually a very long list of things, but that is among them, yeah. Yeah.
At some point, you show the time structure of your neutrino flux. And my question is this important because of supernova connection, or, who cares about time structure in your source?
Well, we actually, it's a nuisance. Let's see, where did I pass it? I think ideally what we'd like, well, I guess it depends on what you want, but our particular source, which has about 1 GeV, a little bit more than 1 GeV, where is that? There it is. Okay, our source has about 1 GeV protons, which is such that you don't make a lot of kaons, you're below kaon threshold. You don't get very much decay in flight. Almost every single pion stops, and that's sort of an ideal, because then if we know that every single pion stops and decay's rest, then we know exactly what the spectrum is. And in fact, that's a 99% true statement. We do have a 1% level of this other scruffy stuff down here. I think this is muon capture. This one is kaon. You get a little tiny bit of kaons in there. Some of this is decay in flight, so there's other stuff there. That, from our point of view, is a nuisance, but we can't help it. We don't get to choose. I guess there's the saying, you don't look a gift horse in the mouth. We got this fabulous source, and this is maybe a tiny annoyance. There are some stop pion facilities, like for instance JPark, MLF at JPark has 3 GeV protons, and they have much more of this stuff out there by actually some orders of magnitude. And in fact, they have quite a bit of this KDAR peak there. And you can actually turn that to your advantage by looking for, this is another monochromatic line that can be used for physics purposes. So it depends what you want to do. For the physics that we're going after, what our ideal is a lovely, clean, scruff-free spectrum. We can live with this at the 1% level. This is not a problem.
Yes, but from the supernova point of view, is also important detailed or less?
It's not. So we are in the foreseeable future statistically dominated. So in a very long-term future where we have much larger detectors, where we're worrying about uncertainties from higher energy, and this it is somewhat overrepresented in the sense that the cross-section is typically scale is E squared, so at higher energy you get somewhat more of them, but it's still pretty small. This is not going to be a big deal for any near future supernova measurements. But eventually, I would actually love to be in a situation where we have enough statistics that we have to worry about that. Yes, this is flux. Yeah, that's right. So this is in fact somewhat overrepresented, but it's still not even close to our largest uncertainty. For the seven scales of z squared as well, but it's still small enough we don't worry about it.
I have a question, a comment. The question is, so you show that you are going to measure iron 56?
Yes.
So that's an interesting measurement.
It is interesting. Actually, we have data. We have 4 years of data in the can. Nobody has analyzed it. So
okay.
It's waiting for the right student to analyze it. Yes.
Okay, so you expect to have a precision which is better than one obtained by Carmen a long time ago? Because Carmen measured it with a pretty low precision, and indeed there were.
Question. I mean, it's a pretty low. It's expected to be a much lower rate than lead. And it's not charge current. It's only it is charge current, but it's only the nins. It's only.
Yes.
And so we expect. I would expect it to be statistically dominant. And actually, I don't know the exact answer. Is it going to be better than 50%? It might be. I mean, it depends maybe what the answer is.
Okay.
But yes, no, we just haven't analyzed that yet.
Okay, and then the neutrino lab, you will measure the neutron emission. So you would measure one emission.
So the lead glass will measure the lepton. We'll measure the.
Yeah, but the cross section. You said you would measure the neutron emission.
We have.
Okay.
Have that. In fact, I think I have that as
the neutron emission.
Yes,
the
and
one
it's
and two neutron emission.
The neutron, not the difference between 1 and 2, but I wonder if I have it in a backup. I might have put it in a backup. I can certainly show it to you.
Okay.
But yes, we have measured the NIN. We call that NIN, neutrino-induced neutron cross section for lead, and it is anomalously low. It's consistent with 0.
Oh.
It's I wonder if I have it here somewhere. In fact, I know you're probably interested in it. Here it is. So this is actually the thesis of Sam Hedges, and this was I grabbed this slide as a backup from another conference, but in fact it's quite low.
Low.
Here it is. Yes, the best fit is 0.3 plus 1.7 minus plus 0.17 minus 0.17.
I see.
So it's.
I see.
Yeah, and we
surprisingly
a possible explanation for that is this is why we're going for the lead glass is that we are only sensitive to neutrons above about 1 MeV, and so if for some reason that we can't think of why the neutrons are softer than predicted, then that would also cause a suppression.
Okay.
And so and to disambiguate that, if we can actually measure the electron in a lead glass detector, then that would in principle solve the problem, or at least understand whether the suppression is just because of the actual cross section or because of the neutron energies.
And my comment concerns the fact that measuring these neutrino nucleus cross section, incoherent neutrino nucleus cross sections, is also important on a range of nuclei, because you can learn about the quenching of the forbidden transitions.
Yes.
Not the allowed ones, but you have a significant contribution from forbidden transitions, and the role of quenching is completely unexplored. So systematically measuring this cross section is important also for this.
Yep. And so in fact our measurement on iodine 127 is also low. Actually, the neutron emission cross-section is low. We can actually, by the energy of the lepton, by fitting the energy spectrum, we can actually gain some information on the single and or the 0 and 1 neutron. We can't go as far as 2 neutrons, but the 0 and 1 neutron emission. So we can get some information from fitting the energy spectrum. And what we see here is that the 0 neutron is not really very low, but the 1 neutron is quite low. And indeed, this is also potentially interesting for understanding underlying couplings as well.
Yeah. Okay.
And
Thank you.
we're doing more of this as well. Yeah.
Thank you very much. I think these measurements are very interesting.
Maybe a question, just very similar one. So somehow, you do not have any cross-section in neutral current where you can measure the spectrum. You just measure above a certain threshold. Am I right or wrong?
Well, we can measure neutral current in principle.
You could, I know that you measure neutral current, but you measure spectrum.
The spectrum is, no, the spectrum is harder. Well, we can measure the semblance, we can measure the recoil spectrum.
Yeah.
But for the inelastic, that's very hard. It's only...
Yeah. So in the sense, in order to learn on the neutral current, say neutrinos from supernova, whatever, you like to have it, and you can rely only on different, say, measurement with different nuclei or something like Christina was telling.
Yeah, but it's true. The neutral current, you typically just get a DX statement. Now you can, if you have neutral current reactions with different thresholds, you can statistically get some information, but event by event, it's not really possible.
Okay, so if there are no more questions or comments, let us thank Kate again.